In August of 1984, something very strange and terrifying occurred in a remote part of Africa. Lake Manoon, a small bone shaped lake located in a rural area of Cameroon, was the scene of a horrifying and unprecedented event. The lake, surrounded by farmland and with a small village to its northeast and a local road just to its east, had always been a quiet, rustic, and relatively obscure place. That peaceful image shattered one night. Late one night in August, local villagers reported hearing a loud, rumbling sound coming from a direction of the lake. At the time, most people didn't think much of it. Then, at around 11:30 p.m., a mysterious white mist suddenly shot up out of Lake Manoon. The mist quickly spread across the nearby road to the east of the lake, forming an eerie cloud that lingered throughout the night. By sunrise the next morning, the cloud was still present. Villagers from the nearby town began waking up and heading to work, traveling along the same road now covered in mist. Mistaking it for an unusual morning fog, they walked or drove straight into it. Tragically, once inside the cloud, they found themselves unable to breathe. Victims would gasp for air, suffocate, and collapse within a minute of exposure. The deadly nature of the cloud was only realized later that morning. By around 10:30 a.m., winds finally dispersed the mist. What it revealed was horrifying. Numerous bodies lying along the road where people had unknowingly walked into their deaths. Eventually, a local police officer and a doctor arrived at the scene. Their investigation uncovered the grim toll of the event. 37 people had died from the mysterious cloud that had silently crept from the lake. Bodies were strewn across the road, people who had been killed by the mysterious mist. Some were found on foot, others slumped over in their cars, and at least one man was discovered dead atop his motorcycle. All had made the fatal mistake of walking or driving through what they believed to be a harmless morning cloud. In the immediate aftermath of the tragedy, there was no clear explanation for what had occurred. Some superstitious villagers believed that Lake Menon was cursed, inhabited by evil spirits that had emerged to claim the lives of the victims. The Cameroonian government, on the other hand, initially suspected a chemical weapons attack, possibly carried out by terrorists or rebels attempting a coup d'etat. However, that theory didn't hold up under scrutiny. Chemical weapons are not easy to obtain, and it seemed highly unlikely that a rebel group would waste them on a remote rural road rather than a high value target. Furthermore, no one had claimed responsibility for the attack. With the chemical weapons theory appearing implausible, investigators turned to the possibility of a natural cause. Attention soon focused on the Cameroon volcanic line, a chain of volcanoes and islands stretching from the Gulf of Guinea inland through West Africa. Lake Manoun happened to lie directly above one of the volcanoes in this chain, long believed to be dormant. But what if it had reactivated? To explore this theory, the American Embassy in Cameroon summoned an expert, Dr. Haraldur Sigurdsson, a renowned Icelandic volcanologist and geochemist from the University of Rhode Island. Many months after the incident, Sigurdsson arrived in Cameroon to conduct a thorough investigation into what had happened at Lake Manoun. He carried out a wide array of scientific tests in search of answers. However, Sigurdsson quickly discovered that there was no evidence of a volcanic eruption in the area. Even more frustrating, there was very little physical evidence of anything unusual occurring naturally in the lake that could explain the sudden deaths of 37 people. The lake bed beneath the surface showed no signs of disturbance. Sigurdsson found no sulfur compounds, an indicator of volcanic activity, and no evidence that the water temperature had recently increased. The first real breakthrough came when he collected a water sample from deep within the lake. As the sealed bottle reached the surface, its cap suddenly popped off, much like a shaken bottle of soda. That moment was a revelation. Sigurdsson realized that the deeper layers of Lake Manoon were saturated with dissolved carbon dioxide, CO2, much like a massive, natural bottle of carbonated water. This insight helped him make a critical connection. The symptoms and sudden deaths of the 37 victims were all consistent with carbon dioxide asphyxiation. In its gaseous form, CO2 is colorless, odorless, heavier than air, and lethal. That explained why the deadly cloud had hugged the ground for so long. It simply sank and stayed low, suffocating anyone who walked or drove through it. With this discovery, Sigurdsson began expanding on his theory. He sought to understand how so much CO2 could have become trapped in the lake, and how it could suddenly be released as a deadly cloud. Over the next 2 years, he steadily developed his explanation. He concluded that Lake Manoon was an extraordinary and rare geological anomaly. He theorized that magma deep beneath the lake bed had been slowly degassing for decades or even centuries, releasing carbon dioxide that percolated upward into the lake. The gas dissolved into the cold, dense water at the lake's bottom and remained there, trapped beneath the lighter, warmer layers of water above. In most lakes, seasonal temperature changes cause the layers of water to mix regularly, which prevents the buildup of gases like CO2.
During winter, surface waters cool, become denser, and sink, pushing the deeper, warmer layers upward. In spring and summer, the process reverses, constantly stirring the lake and releasing any accumulating gases. However, Lake Manoon lies near the equator, within the tropics, where the climate stays warm year-round. Because of this, the typical seasonal mixing of lake layers never occurs. As a result, the lower layers of tropical lakes can remain stagnant for centuries, allowing dangerous concentrations of CO2 to silently build up over time. Sigurdsson theorized that, in the specific case of Lake Manoon, this long-term CO2 accumulation had reached a critical point, just waiting for the right trigger to unleash disaster. Over time, the colder, denser bottom layer of Lake Manoon had become increasingly saturated with dissolved carbon dioxide. This dangerous buildup remained trapped by the warmer, lighter surface water above it, acting much like a cork sealing a bottle of champagne. Sigurdsson theorized that once this cork was disturbed, or once the CO2 concentration in the bottom layer reached a critical threshold, the entire balance of the lake could be violently disrupted. The two layers would suddenly mix, and all the trapped CO2 would erupt upward in gas form, creating a lethal cloud capable of suffocating anything nearby. In essence, Lake Manoon had likely been a silent, hidden time bomb for centuries, its danger completely undetectable to the villagers living around it. Sigurdsson referred to this scenario as a previously unknown type of natural hazard, one with the terrifying potential to annihilate entire towns. In 1986, 2 years after the Manoon disaster, Sigurdsson submitted his full theory to the prestigious journal Science. But to his frustration, it was rejected, dismissed as too far-fetched. As a result, his theory remained relatively obscure, known only within a small circle of volcanologists and geochemists. But that would soon change, dramatically. Astonishingly, just about 100 kilometers to the northwest of Lake Manoon, another lake in Cameroon, Lake Nyos, harbored a similar unseen danger. Coincidentally and terrifyingly, this second time bomb was also nearing detonation, and when it finally erupted, it would be exponentially more deadly than what had occurred at Lake Manoon. As the sun set on August 21, 1986, the quiet villages surrounding Lake Nyos were completely unaware of the catastrophe about to unfold. Around 9 p.m., a few of the very few people who would survive later reported hearing a loud rumbling noise, eerily similar to reports from the Manoon incident. Most villagers had already gone to bed, unaware of the danger. Then, suddenly and with almost no warning, a massive eruption of gas occurred, a cloud of up to 1 cubic kilometer, equivalent to 300,000 tons of carbon dioxide. burst out of Lake Nyos in the form of a thick, low-lying white mist. Scientists who later investigated the site discovered that the eruption may have even triggered a localized tsunami, with waves up to 25 meters high crashing against one of the lake's shores. The gas cloud initially shot upward at a terrifying speed, nearly 100 kilometers per hour. But because CO2 is heavier than air, it quickly collapsed and spilled outward from the lake's rim, pouring down into the surrounding valleys where unsuspecting villagers lived. The cloud of carbon dioxide surged out from Lake Nyos and rolled down into the surrounding valleys, sweeping through multiple villages and carrying death as far as 25 kilometers from the lake. In the two villages closest to the eruption, Nyos and Cha, only 4 people survived. Their sole advantage, they had been located on higher ground, above the path of the low-lying toxic mist. In some cases, a few people in other nearby villages were fortunate enough to be rendered unconscious by the CO2 cloud rather than killed outright. Some of them remained unconscious for up to 36 hours, only to awaken to an unimaginable horror, their families and neighbors all dead. Those who survived often suffered long-term health consequences, severe respiratory issues, inflamed skin lesions, and even paralysis in extreme cases. Over the next few days, survivors and residents from more distant towns cautiously entered the valleys surrounding Lake Nyos. What they found looked apocalyptic. The gas cloud had claimed the lives of 1,746 people, nearly 50 times more than the Lake Manoun disaster just 2 years earlier. It had swept across the land like a biblical plague, sparing neither humans nor animals. Roughly 3,500 cattle perished in the cloud, their lifeless bodies scattered across the region alongside the human dead, deepening the overwhelming sense of devastation. Yet, among the most chilling details reported by those who came upon the scene was the silence. There were no flies buzzing around the corpses, not a single insect alive. The CO2 cloud had been so potent and deadly that it had annihilated nearly all life in its path, down to the smallest creatures. It was a localized extinction event, a sudden and terrifying wipeout of an entire ecosystem. To complete the surreal, hellish scene, the waters of Lake Nyos, normally a calm and scenic blue, had turned a deep, rust-colored red. Scientists later explained this was due to iron-rich water from the lake's depths being churned upward during the eruption, oxidizing upon contact with the air. The sheer scale and horror of the Lake Nyos disaster instantly drew far more global attention than the earlier tragedy at Lake Manoun. Sigurdsson's once-dismissed theory of lethal gas eruptions from deep tropical lakes was now seen in a grim new light. What had once been considered too far-fetched was now undeniable. In the weeks and months that followed, scientists and researchers from across the world rushed to Cameroon to investigate the disaster. They descended on Lake Nyos in droves, determined to uncover how this could have happened, and more importantly, how to prevent such a catastrophe from ever happening again. As scientists and researchers pieced together the evidence at Lake Nyos, a familiar pattern began to emerge, eerily similar to the Lake Manoun disaster 2 years earlier. Like Manoun, Nyos was a tropical lake sitting above a volcanic region with a stratified water structure. A colder, denser lower layer saturated with dissolved carbon dioxide, CO2, and a warmer, lighter upper layer acting as a cap. Over potentially centuries, CO2 had seeped into the lake's bottom layer from deep volcanic springs, building up unnoticed until it was ready to violently escape. While the exact trigger of the 1986 eruption at Lake Nyos has never been definitively confirmed, the leading theory is that a landslide may have caused it. Some surviving villagers reported hearing a loud rumbling or crashing sound just before the deadly gas cloud appeared, consistent with the idea of boulders plunging into the lake. Supporting this, several researchers observed signs of a recent rock slide on one of the cliffs surrounding the lake. Other theories have been proposed as well. Some scientists believe that a sudden drop in air temperature could have cooled the lake's surface waters, causing them to sink and disrupt the stability of the layers, resulting in the sudden release of gas. Others suggest that a strong gust of wind or a period of heavy, cool rainfall might have stirred the lake just enough to trigger the eruption. Regardless of the exact cause, what was undeniable was that Harold Sigurdsson's theory, initially dismissed as speculative, was now proven to be a real and terrifying natural hazard. These events became classified under a new term, limnic eruptions, a phenomenon where CO2 gas erupts violently from a deep lake, suffocating life in the surrounding area. The realization that such disasters were not myths or isolated freak incidents was chilling. Even more troubling, the scientific teams discovered that the 1986 eruption at Lake Nyos had not expelled all of the lake's trapped CO2. Significant concentrations of gas still remained in the lower layers. The same was true at Lake Manoon. In other words, both lakes could erupt again, with potentially equally deadly results. This posed a massive and urgent risk to the thousands of people still living around them. Faced with the threat of future explosions, scientists proposed several ideas to remove the accumulating CO2. Some were more extreme than others. One early idea even involved dumping vast amounts of lime into the lakes using helicopters, in the hope that the chemical reaction would neutralize the dissolved gas. While conceptually interesting, it was quickly deemed impractical and too costly to be realistic. To neutralize the threat of future limnic eruptions, a number of proposals were put forward by scientists and researchers. One idea involved dumping large amounts of lime into the lakes to chemically neutralize the dissolved carbon dioxide. However, this approach was deemed far too expensive. Another proposal suggested detonating bombs inside the lakes to forcibly eject the CO2, essentially simulating a controlled eruption, but this was rejected as too dangerous. Yet another idea involved digging channels or tunnels beneath the lakes to drain the CO2-heavy water out from the bottom layers, but this too was ultimately dismissed due to its extreme cost and complexity. Eventually, the researchers agreed on a much simpler and more cost-effective solution. In 2001, a floating platform was installed on each lake with a long vertical pipe reaching down into the CO2-saturated lower layer. This pipe allowed the gas-rich water from the bottom to slowly rise to the surface. As it ascended, the pressure decreased, causing the dissolved CO2 to form bubbles and vent out harmlessly into the atmosphere. It was essentially a controlled, continuous mini-eruption, a safe and steady degassing process. Over time, additional pipes were installed to increase the degassing rate. By 2009, Lake Manoun was declared fully degassed and no longer at risk. Lake Nyos, being much larger and more dangerous, took longer, but by 2019, it too was considered safely degassed and stable. These efforts were hailed as major successes in preventing further disasters caused by this newly recognized natural hazard. However, just as these two deadly lakes were being neutralized, scientists identified a third lake in equatorial Africa with the exact same conditions and with the potential to be far more catastrophic. The set of criteria required for a lake to be vulnerable to limnic eruptions is extremely specific and rare. These lakes must be located in equatorial regions to prevent seasonal mixing of water layers, lie above tectonically or volcanically active zones, be situated at moderate altitudes, not cold enough to disrupt thermal layers, and be deep enough to allow stable layering of gas-saturated water over long periods. These conditions are so uncommon that since the 1980s, only one other lake in the entire world has been found to meet them, Lake Kivu. Located on the border between Rwanda and the Democratic Republic of the Congo, DRC, Lake Kivu is part of the African Great Lakes region and dwarfs both Lake Manoun and Lake Nyos in size. While Lake Nyos is just 1.7 kilometers long and about 213 meters deep, Lake Kivu is a giant, stretching 88 kilometers long, 48 kilometers wide, and reaching depths of 475 meters. Its enormous size and gas content make it potentially the most dangerous lake in the world. Similar to how Lake Manaun and Lake Nyos lie along the tectonically active Cameroon volcanic line, Lake Kivu sits atop another geologically unstable area, the East African Rift Valley. This massive rift is a region where the African continent is slowly being torn apart by tectonic forces, a process that will eventually, in several million years, result in the formation of a new ocean. These immense subterranean stresses have thinned the Earth's crust beneath the region and triggered volcanic activity, which includes CO2-rich hot springs bubbling up into the lake's lower layers, just like at Nyos and Manaun, but on a far greater scale. Lake Kivu is also geologically much older than either Lake Nyos or Lake Manaun, which has led to the accumulation of rich organic sediments in its surrounding soils. Down in the lake's deeper, colder layers, vast colonies of microorganisms feed on this organic matter and, in the process, produce significant amounts of methane. On top of that, the volcanic processes underneath the lakebed may also be contributing additional methane into the water column, something that was completely absent at Nyos and Manaun. This combination of methane and CO2 makes Lake Kivu vastly more dangerous than its two Cameroonian counterparts. For one thing, methane is much less soluble in water than CO2, which means it reaches saturation far more quickly. This raises the risk of a sudden, spontaneous degassing event occurring with little warning. Even more concerning, methane is also highly flammable. If an eruption were to occur at Lake Kivu, the released cloud could consist of both toxic CO2 and flammable methane, a deadly cocktail that might not only suffocate life in the region, but also ignite, producing a massive fiery explosion that could devastate the surrounding area. Like Lake Nyos, Lake Kivu's deep waters are divided into distinct density layers. The lower, cooler, and heavier layers are where most of the methane and CO2 are trapped. These are capped by the upper, warmer, and lighter layers, which act like a cork on a gigantic bottle of carbonated gas. These layers are separated by thin boundaries, sometimes just a few centimeters thick. Because of the consistently warm equatorial climate, the lake never experiences the seasonal turnover seen in more temperate lakes. As a result, these layers remain stagnant for centuries, allowing dangerous gases to accumulate to unprecedented levels. Lake Kivu is a steadily building time bomb. Beneath its surface, the concentrations of dissolved CO2 and methane continue to grow, increasing the pressure on the lake's lower layers. Like at Lake Nyos and Lake Manaun, there are multiple potential triggers that could cause a catastrophic eruption. One possibility is that the CO2 or methane reaches its saturation point, meaning the lake water can no longer hold any more gas in solution. At that point, even a small additional amount of gas entering the layer could cause it to bubble out of solution, rise rapidly to the surface, and trigger a violent degassing eruption. Another potential trigger is a large kinetic event that causes the lake's deep, gas-rich layers to mix with the upper, lighter layers. This mixing would reduce pressure on the lower layers and force the gases to rapidly escape. Although a simple landslide, like the one suspected at Lake Nyos, might not be large enough to trigger such a massive lake, Lake Kivu is so vast that it would likely require a much larger disturbance to initiate an explosion. In a region as seismically active as the East African Rift, this is far from impossible. Earthquakes are frequent in the area, usually ranging between magnitude 4 and 6 on the Richter scale. However, stronger quakes do occur. In 2008, a magnitude 5.9 earthquake struck the western shores of Lake Kivu, while in 2005, a 6.8 magnitude quake hit nearby Lake Tanganyika on the DRC-Tanzania border. Even more powerful, in 1990, a 7.2 magnitude earthquake struck near Juba in modern-day South Sudan. If a major quake were to hit the Lake Kivu area directly, it could create powerful internal waves and disrupt the lake's stratified layers, potentially triggering the massive release of CO2 and methane gases stored in the depths. Even more alarming is the possibility of an extreme drought caused by climate change. If Lake Kivu's water levels were to drop significantly, the natural cork effect that the upper layer provides would weaken. A sudden, intense rainstorm during such a drought could create a violent disturbance that might trigger a limnic eruption. In this sense, climate variability could make the lake even more vulnerable in the future. Regardless of the cause, if Lake Kivu ever explodes, the results would be unimaginably apocalyptic. The Lake Nyos disaster in 1986 released about 1 cubic kilometer of CO2 and killed over 1,700 people. By contrast, scientists estimate that Lake Kivu's lower layers contain approximately 3,000 cubic kilometers of dissolved CO2, along with around 60 cubic kilometers of dissolved methane. This is thousands of times more gas than was released at Nyos, and it's situated near high-density population centers. The scale of devastation would be unprecedented. Lake Kivu is estimated to contain around 2.66 gigatons of dissolved CO2 in its deep waters. To put that into perspective, if this volume of gas were suddenly released in a limnic eruption, it would unleash, in under 24 hours, the equivalent of approximately 5% of the entire planet's annual greenhouse gas emissions, all released in just one small region. This would be a massive environmental catastrophe on top of the already devastating human toll. Even worse, the areas surrounding Lake Kivu are far more densely populated than those around Lake Nyos or Lake Manaun. Today, more than 2 million people live along its shores, including 2 major urban centers on the lake's western edge, Bukavu and Goma, each home to hundreds of thousands of residents. If Lake Kivu were to erupt in a similar fashion, the resulting disaster could kill millions of people within a single day, making it potentially the deadliest natural disaster in recorded human history. Despite the clear danger, there's still considerable scientific uncertainty about how often Lake Kivu has erupted in the past, or even if it ever has. Sediment cores taken from the lake reveal 9 distinct brown layers, which may represent past mixing or eruptive events. However, the interpretation of these layers varies significantly among scientists. Some argue that the layers show evidence of mixing in the past 2,000 years, but not of a full-scale limnic eruption, at least not within the last 12,000 years. Others contend that a limnic eruption did occur roughly 4,000 years ago, suggesting that such an event could be geologically recent and might happen again. Adding to the complexity is ongoing debate over the timeline of risk. In 2005, 2 environmental scientists, Martin Schmid and Mikkel Halvax, published a paper comparing gas saturation levels in Lake Kivu's lower layers with measurements from 1975. Their findings suggested that methane concentrations had increased by about 15% over those 30 years. If that rate of buildup were to continue, they predicted that Lake Kivu's lower layers could reach full methane saturation by around the year 2090, potentially triggering a catastrophic eruption. However, a more recent study from 2020, co-authored again by Martin Schmid, complicates the picture further. That 2020 study suggested that methane levels in the lower layers of Lake Kivu may not have increased at all over time. But again, no one is really sure. The findings are controversial. Some scientists argue that the study didn't actually prove methane levels have remained stable, only that no detectable change was observed, which isn't the same thing. In other words, the uncertainty remains. We still don't fully understand what's happening under the surface of Lake Kivu. Many proposals have been made by scientists and researchers on how to make the lake safer. However, the sheer size of Lake Kivu makes this a far more complex and challenging task than what was required at the much smaller Lake Nyos or Lake Manaun. And unlike those lakes, which are located in relatively quiet regions of Cameroon, Lake Kivu sits in the middle of a highly volatile and dangerous geopolitical conflict zone. The western shore of the lake, which lies in the Democratic Republic of the Congo, DRC, is currently outside of the DRC government's control and is dominated by non-state rebel factions. The most powerful of these groups is M23, a rebel militia that is widely believed to receive direct support and weaponry from neighboring Rwanda. In recent years, M23 fighters captured the cities of Goma and Bukavu, the largest urban centers along the lake, and killed thousands of civilians in the process. This chaotic and violent situation makes monitoring gas levels and seismic activity on the western side of Lake Kivu nearly impossible. With the area effectively a war zone, the DRC government has no access, and the lake's most dangerous side remains largely unmonitored. Fortunately, Rwanda maintains a relatively robust gas monitoring infrastructure on the eastern side of the lake, including systems for tracking CO2, methane levels, and seismic events. While this does provide some measure of oversight, it also highlights the imbalanced monitoring coverage across the lake. Still, any sudden gas release or pressure shift would likely be detected from Rwanda's side. Eventually, the Rwandan government came to view the lake's massive methane reserves not only as a threat, but also as an economic opportunity. Since methane is a valuable fuel that can be burned to generate electricity, Rwanda launched a pilot project in 2008 to begin harvesting it. Then, in 2015, a far larger effort was launched, the Kivuwat project. Kivuwat is a privately owned British company that operates on the Rwandan side of the lake with official government backing. The project, which cost over $200 million to get off the ground, established a complex system on Lake Kivu to extract methane-rich water from the lower layers, separate the methane gas from the water, and then pipe the methane to power plants on land, where it is burned to produce electricity. The methane-free water is then safely pumped back into the lake's lower layers, accomplishing two critical objectives. For Rwanda, the methane extraction project offers a crucial dual benefit. It provides a much-needed source of fuel for electricity generation, and it also gradually reduces the risk of a future limnic eruption by slowly removing methane from the lake. Currently, the Kivuwat Phase 1 operation supplies approximately 26 megawatts of power to Rwanda's national electricity grid, accounting for around 9% of the country's total electricity supply. Looking ahead, the company plans to expand its operations to eventually generate over 100 megawatts, which would represent nearly one-third of Rwanda's current total energy supply. That makes Kivuwat a cornerstone of Rwanda's national development strategy. However, the rate at which methane is being extracted from Lake Kivu is very slow. At its current pace, Kivuwat is expected to remove less than 5% of the lake's total methane over the next 25 years. And there's growing concern in the scientific community that projects like Kivuwat could, ironically, increase the risk of a limnic eruption, the very catastrophe they are designed to prevent.
Some researchers warn that the physical disruption caused by the methane extraction process may disturb the delicate stratification of the lake. The layers of Lake Kivu are separated by just a few centimeters thick boundaries, and critics argue that drawing gas-rich water up from the bottom might puncture these barriers, allowing the heavier, gas-laden water to rise, mix with upper layers, and trigger a runaway chain reaction. Other scientists believe that the full environmental consequences of methane extraction from Lake Kivu might not become apparent for decades, and that the risks may outweigh the potential benefits. Still, there are many researchers and policymakers who believe the opposite, that the Kivuwat operation is safe, tightly regulated, and essential.
For a low-income, energy-constrained country like Rwanda, having a domestic renewable energy source like Lake Kivu's methane is a rare and valuable asset, and potentially a model for balancing risk management with economic development. Whatever the case, one fact remains clear. Blake Monoon revealed to the world that limnic eruptions were real. Wait, Lake Nyos revealed just how deadly they could be, and now Lake Kivu looms as the most dangerous of all. Despite its serene surface, Lake Kivu harbors a vast hidden reservoir of explosive potential, and with millions of people living along its shores, including in regions mired in violent armed conflict, the possibility of a catastrophic limnic eruption remains one of the most terrifying natural disasters silently waiting to happen. Regardless of how likely it is, the fact that it could happen at all, and the scale of devastation it could bring, makes Lake Kivu arguably the most dangerous lake on Earth. While it's definitely concerning to live near a lake like Lake Kivu, it's also worth pointing out that living in the United States comes with its own set of serious privacy risks, ones you might not even be aware of. The truth is, America has some of the weakest data privacy and protection laws in the developed world. Compared to other countries, a staggering amount of your personal information is collected and made public, sometimes even by federal, state, or local governments themselves. This has always been true to some degree, but it didn't become a serious issue until the rise of the internet. That's when data brokers stepped in. These are private companies that collect and sell your personal data, often by scraping public records like voter rolls or census databases. And there are hundreds of these companies out there, probably selling your personal information right now. They might have your name, phone number, home address, shopping habits, or even your social security number. All available to the highest bidder. When I checked myself, I found hundreds of data brokers offering my personal information for sale to advertisers, scammers, stalkers, or worse. At best, this results in a flood of spam calls and junk emails. At worst, it can lead to phishing attacks, identity theft, or doxing. And if you live in the US, there's no comprehensive federal law protecting you from this kind of data harvesting. And as always, thank you so much for watching.